So I have no idea. We'll just go ahead and start today. We started talking about very briefly about binary search trees and the basic operations. And I was just going to take the rest of the day here and we're going to implement them all. So as a reminder, here's a binary search tree. Everything has a key, and everything in the left subtree is less than that key. Everything in the right subtree is greater than that key. And so the way that you go about searching a binary search tree is, of course, you start at the root. And if the thing that you're searching for, if you find it, great. Otherwise, if you don't find it, the thing that you're searching for is less, then you go to the left. Otherwise, you go to the right. So obviously, you only have to go as deep in the tree as the depth of the tree. And so you'd have 1, 2, 3, 4, 5, 6, at most 6 comparisons here to find the thing the deepest in the tree, or at least to find that the thing doesn't exist. For example, if you're searching for 13, if it exists, would exist right here, but it doesn't, so we return a unsuccessful search, right? And then we went through, well, how do you add something to a binary search tree? Well, you find out where it belongs, right? If you want to add 28, well, it's already in there, then that's no operation. And so if you want to add 13, you'd find out where it would belong, and then you just simply add it there as a new leaf. And then we went through a couple of different cases for deleting something, right? If we're deleting a leaf, well, that's no big deal. We just sever it off from the rest of the tree. If you're deleting an internal node, but it only has one child, that's easy too, because then you can take that child and promote it up and effectively go past that node there, right? But if you have 2 children, say you wanted to delete 50, right? Well, you can't just substitute one or the other child, because then that would mean it potentially has up to 3 children. So the strategy would be that you go to the left subtree and you find the largest element there and you promote that up and replace 50 with it. And that's guaranteed to have only one child, because if it didn't and there was something else over here, then that wouldn't be the maximum. Right? Likewise, what you can do is you can go to the right subtree and find the minimum element, in this case 60, and we know how to deal with that because, again, it's at most one child. Okay? So with that in mind, let's go ahead and spend the rest of the day implementing our own binary search tree. I'm not going to put it into an inheritance with that binary tree, simply because for the same reason that a list and a sorted list, do they belong in an inheritance hierarchy? If a sorted list is a list, then that means that you inherit all of these methods that potentially can screw up the sorted list, like add to an arbitrary index or something like that, violating the Liskov substitution principle in the solid principles, right? It's the rectangle square problem. So I'll just call this binary search tree, right? There we go. And you'll note here that I've immediately parameterized it, okay? We're not just going to hold integers. We're going to work off of this example, which is integers. But immediately here, I want the binary search tree to hold any type of element, okay? Like the binary tree, we're going to have a private tree node, that's also parameterized on the same type, and that's my root. We can keep track of the size. We'll come back and do that later, though. What else are we going to need? Well, maybe we can come back to it and decide. But I'll go ahead and make a public constructor here, and this .root, we'll let that be null, okay? Let's go ahead and do that first. Now, we have not built a tree yet, so I have no idea what's in here. But of course, we're going to want it to have an add method, right? Add element of type T. I'll just call it X. And we're probably also going to want to have a find method. Now, unlike a list where I want to know what index it's available at, indexes don't make any sense with respect to a tree. So what's a function that I could have, or what's a pattern that I could have for a binary search tree to find something? Maybe return a Boolean that it actually contains that element. t sub x. All right. Let's go ahead and do that one first. Contains. Help me out. Contains an element of type x. All right, well, how do we search the binary tree again? We start at the root, and if that's what we're looking for, we're done. Right? Otherwise, if it's not what we're looking for, we either go left or go right. Go left or right, left or right, left or right, until what? We've either fallen off the edge of the tree, in which case it's an unsuccessful search, and we return false, it does not contain that element, or we find what we're looking for and we return true. Okay? So I'm going to start at the root and keep track of my tree node here. Tree node T. I'll call it current, and I'll start it at the root. Okay? Now, I will put it, I'll go ahead and start it with a while loop here, that while the current is not equal to null, then I will continue traversing left or right to find what I'm looking for. Otherwise, if I break out of this while loop and I've fallen off the edge of the tree, right? I'm searching for 13, but it doesn't exist. And so current will end up being null. And once I'm out of that loop, I will go ahead and return false. It does not contain that element. Okay? Now here's where all the magic is, right? While loop. While the current is not equal to null, what do I want to do? I want to look at the thing stored in current. Right? So let's go ahead and grab that element, right? Item is equal to current dot get item. Right? Now, if x is equal to that item, then I need to stop and return what? True. Right? Otherwise, if x is less than that item, I need to traverse left. Else, if x is greater than that item, then I need to traverse right. There we go. But now I immediately run into a problem here. Can I use less than? Can I use greater than? Can I use equals equals? When, what is my type of x again? It's of type t. It's parameterized. So given two things that I don't know what they are, how do I compare them? A comparator of elements of type T. And I'll just call it CMP for short. Right? And I'm going to make it final so that you can only set it once and you can't change the ordering. Right? It would be weird if you were holding integers and then you inserted 100 integers in ascending order, and then suddenly you change it to descending order, right? That ain't what that tree is, okay? So how do I get this comparator into my binary search tree? How do I get anything into an object? Through its constructor, right? This dot CMP is equal to that CMP, okay? All right, that solves this. Now, how do I use that comparator to make a comparison between the two items? And if they're equal, then I immediately stop and return true. This .cmp.compare, I'm going to compare x and the item. And if that is equal to what, do I know that they're equal? So do you remember the pattern of a comparator? Hopefully we just have that committed to memory because it's in every single programming language, period. Right? Something less, or is less than 0. Something negative if they're in order, positive if they're out of order, and 0 if they are equal. And so if I want to compare them and say that x comes before item, then it's going to be compare x comma item, and if that's less than 0. There's the pattern that you follow, right? Did you see the change there? So let's go ahead and write the original line here. Else if x is less than item, then do this, right? So if you always write it like less than, and then keep x here, and item on the right side, x is on the left side, item is on the right side, and you use a strictly less than sign here, then all you're doing is putting a 0 onto the other side. Right? So follow that pattern over and over and over again. Right? In this case, it will be else if. Now, actually, strictly speaking, do I need to have an else if here? It's either equal, or it's strictly less than, or it's strictly greater than. I don't need that at all. There we go. All right, how do I traverse left? I've got a current node, right? Will be currents dot get left child. There. Current is equal to traverse right, current dot get right child. There you go. Spell it correct. And there you go. Okay. Well, that seems useful, but maybe we can expand this out to a more useful function. For example, what if all we're doing here is returning true or false, right? What if instead I had a public tree node T that said find node, right? Containing the element X. What would that look like? That would look exactly the same, but instead of returning true and false, what do I return? If you find what you're looking for, return the node at which you found it. If you don't find what you're looking for, also return the node at which you found it, because current breaking out of this while loop would be null. You did not find it. Which one of these is more general? Which one gives more information? The find node or contains? Contains only gives you true, false. But find nodes gives you null, not null. And in the case that it's not null, you can have access to the actual node. So which one is more general? Probably find node. So let's go ahead and get rid of this and call that other function, right? Tree node TU is equal to this dot find node of X, right? And then we can set up a condition here. If U is null, then return false. It does not contain that element. Else, return true. Right? So in other words, we can implement this function with respect to this function right here. I don't like 1, 2, 3, 4, 5, 6, 7 lines of code here when we can. Why say many words when few words do the trick, right? Return this find node, and that's equal to or not equal to null. Right? If it's not null, then you found it. If it is null, then you didn't find it. That's a much more elegant solution right there, right? But now it's got me rethinking the design of this find node. What's one problem with making that public? It's a tree node, right? So I'm giving you access to the internal workings of this tree, right? That sounds like a leaky abstraction to me. I've leaked out information about how I'm representing this tree. So let's make it private. You don't need that, right? Unless there's a very, very good reason for you to. You do need this because that's a basic, operation of a binary search tree, right? Okay, great. I still can't test this though because, well, it would only ever work on an empty tree, right? I haven't implemented this add method over here. Nevertheless, let's go ahead and set ourselves up for testing it, okay? So, binary search tree. And I'll go ahead and put in integers just to keep it simple, right? BST is equal to new binary search tree. And let's go ahead and add things to it. bst.add 20, bst.add 10, and 30, right? And then we can ask questions, right? System.out.println, bst.contains 10. It should contain 10 because I put it in there. Does it contain 10, 20, and 30? So I should be getting a bunch of trues out of all of these things. Except, again, what do you need for the binary search tree? A comparator. So how do we create a comparator? Here's the old school way. Comparator for what? For integers. And I'll just call it CMP here as well. New comparator for integers. Right? And We will we'll bring this in, import this. Again, this is an anonymous inline declaration, right? And all we have to do is implement the compare method here. I don't like O1 and O2, those are auto-generated. So let me go ahead and call them A and B, and then I'll return everything that's built in, the basic types, integers, doubles, strings, etc. They're all comparable. So I can go ahead and compare to B using the same exact pattern. Okay? And I'll put that into CMP over here. There. Remind me, and we'll come back and we'll make this even shorter using newer Java, new shiny Java. Okay? All right. So this won't work, of course, because false, 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 because these are not implemented. Right? Add here is not implemented. We now actually have to do this. All right. Suggestions? In order to add 13, we know that 13 is not in there, right? In order to add it as a right child to 12, what do we have to do? We have to search for it, right? Oh, it would, if it existed, it would be here, right? Okay. Say what? We first try to find it, right? And so I've got a function here that does that almost, right? If 13 existed, it would find the node at which it exists, right? So I kind of really want to reuse this code because I don't want to repeat myself and I'm lazy. Right? So initially, let's go ahead and cut and paste it. Right? But here we're not going to find the node. We're going to find the node before it. Find parent node. Right? So if X exists, we'll go ahead and get the parent node. If it doesn't exist, well, if it existed, then here's its parent node. Okay? All right. So how am I going to go about doing this? Yeah, well, okay, so if I have current here, if I had the node in my hand, right, I could just go ahead and go get parent, right? But remember, the purpose of me writing this is that current is going to end up right here, and so can I get its parent? No. So let's whiteboard this. Ideas. Here's current, 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 current. Current gets updated here to say that doesn't exist. What I really wanted was not the current one, but what do we call the current one right before the current? Previous. So let's keep track of two things. Right? Let's keep track of the current node, but also the previous. Now the previous is not going to start at the root. It's going to start out at null. Right? Because the current is going to be the root, but where did we come from? We came from nowhere, so null. Okay. Okay. So we would find it and return current here, except that if we do find it, then we'll go ahead and return the parent, current.getParent. Otherwise, once we have exited this while loop, then that means that the current is null, but the previous is the parent that would have been. Now we do have to be careful here because I am updating current to the left child or the right child, but am I updating previous here? Nope. So what do I need to do? Previous is equal to current, right? You always have current and previous, and as you move along, previous just becomes current. Okay. There's find parent node. All right, there might be a corner case here that we're not thinking about. In fact, what is a corner case that we're not thinking about immediately? Okay, if the tree is empty, right? If the tree is empty, then what do we do? There is no null, there is no root, and so what do we need to do? New root with 20 in it. Okay, so that's one easy corner case that we can take care of here. If this dot root is null, then we need to say that this dot root is equal to new tree node containing t, or x, excuse me. And then immediately return because we're done. That's it. Okay. Okay. Now we just need to find the parent by calling this function here. Right? So this dot find parent node of x. That gives me a tree node. Is the parent. There we go. All right, and how do we set up, go about setting up? So here's the visualization of this, right? I want to create a brand new node with say 13 in it, and I've got the parent. Okay, so let's go ahead and create a tree node t, and I'll just call that child because that's what it is. Is a new tree node t of x. And now I need to set up that parent-child relationship, right? Does it necessarily become a right child? On the example it was, but not necessarily in general, right? Does it necessarily become a left child? Nope. We have to check, right? So which is the case? If this .cmp of x, comparing that with the parent dot get item, right, is less than 0, then that means that it needs to go where? To the left child. So parent dot set left child to child, else if, but it's actually a good question. Actually, no, we'll come back to it. We'll go ahead and leave it like this. Parent dot set right child to child. There we go. All right, it either goes to the left. Oh, what's wrong with you, CMP? Oh, dot compare. There we go. All right. The thing that you're trying to insert, x, is less than the parent's item, so it goes to the left of the parent. Otherwise, it goes to the right of the parent. All right. What else do we need to set up, by the way? That only sets it with respect to the parent. What about 13? Is there a relationship back to the parent? Yep. In our tree node, remember what our tree node looks like? It's got a left child and a right child, but it also has a parent that we need to keep track of, or that we should keep track of for convenience. It's going to happen no matter what, so child.set parent to the parent. Right. And we return. There we go. Let's see if this works. True, true, true. Okay. If I ask for 40, it should be false, right? Okay. All right. How could I be absolutely sure about the structure of that tree, though? I could run a debugger, right? Let's do it the sophisticated way first. And run a debugger and see that here's the binary search tree, right? I don't have a toString method here yet, but there's the root. And what is the item of the root? 20, right? If you inserted 20, 10, and 30, what should it look like? You inserted 20 first, that becomes the new root. And then what did I say, 10? It doesn't matter. 10, 30, 30, 10. It should look like that, right? The left child has an item, 10. And the right child has an item, 30. I'm convinced that that works, but let's be a little bit more rigorous about it. Let me stop the debugger here. All right, and go back to Java mode. There we go. All right. I don't want to make sure that it works just for 10, 20, and 30. Let's kick it up a notch and put in a whole bunch of random values. Right? Trying to break it, when you're trying to test something and you try to throw a bunch of bad data or random data, as sometimes it's called fuzzing, right? You're trying to break it. And so we're going to go ahead and put in a bunch of random data here. For int I equals 0, I is less than 10. I'm just going to go ahead and put in 10 random values between 1 and 100. Right? bst.add r.nextInt, but between 1 and 100, because 0 to 99, because I actually want to read it. I don't want to just see big number, big number, big number. Right? Right. That runs without breaking, but are you are you excited about going through a debugger here? System.out.println. Well, we could print it out. What would that look like? That's going to be the Java virtual machine memory address, right? That's not too helpful. So let's go ahead and run it through a debugger here, and okay, expand the binary search tree. There's the root, and what's its item? 89. Okay, its left child has an item of 72. That checks out so far. That has a left child and a right child, and it's going to be 28 and 89. I forgot. I would be writing this out on a piece of paper. All right. What's an easier, more automatable way of testing this? If I were to enumerate everything in a binary search tree using pre-order, in-order, or post-order, which one would you want most? Which one would be the most useful? In-order, why? Because it's a binary search tree. It's in order. 2, 12, 10, 15, 20, 24, 28, ... So if I had an in-order traversal of this binary search tree, then I'm going to go back over to my binary tree and steal. Right? There's BFS. There's in-order traversal. Stack-based in-order traversal. Right? I think that it worked, didn't it? I don't remember. Right? There we go. I just stole it. And we can go ahead and use that in our tester, because if both of those things are right, then I would expect this to have what was it, in order? There we go. I would expect this to be, yes, it's going to be random, right? But it's going to be in order, right? Public list, what are you griping about? Demo. Oh, okay, I just didn't save it, I guess, yeah. All right, let's run it. Now again, random values, but they'll be sorted. Hey, that looks nice. Different random values. Okay, there's something going on here. Try again. Ah, random values. Are there 10 random values there, by the way? What happened? Okay, so what happens when we have 296s? Apparently, in our design, nothing, right? Or maybe nothing, I don't know. Right. Let's trace our code. So I want to add an element, right? Suppose that element already exists. When we call find parent node, right? And we create a brand new child here, what if it did exist? 45. Oops, sorry. It exists. Yeah, what are we going to do with its old right child and its old left child if it existed? Goodbye. Bug. All right. So let's take care of that as a corner case. Okay. It's not going to be too expensive to go through the tree twice. Or actually, what I could do is, I've already got the parent, right? What could I do? If the item, I could say that before I set the parent here, I don't know. I just need to check. Is X the left or right child of the parent? If so, it exists. Do nothing. ... We just return. Right? So I could write the code to do that pretty easily here. Give myself some room. If parent.getLeftChild.getItem is equal to X, or parent.getRightChild.getItem is equal to X, then just simply return no operation here. Now obviously I can't use equals equals, but I'm not going to leave with this code anyway. Because what happens when there is no left child? For example, I'm deleting 45. There is no left child, so can I get the element? Nope, I would end up having a null pointer exception. So, I have this huge logic. If the left child exists and its item is equal to x, or if the right child exists and its item is equal to x, then do it. Right? That sounds, at that point I'm just going to say, you know what? I have a contains method. If this dot contains, this is cleaner code. You'll risk something here that we'll talk about in a second here. But if this already contains it, then what? Return. Don't do anything. In fact, that should go before the parent there. Right? Now, you are at risk here because you're asking the question, does it contain x? Right? If so, then you immediately return. Otherwise, you traverse the tree again to find its parent, right? If it doesn't exist. One solution that I thought about thought about trying before I came to class today was, you know what? It would be really, really nice if we had a find node and its parent, right? And it returned a tuple, kind of like a Python tuple. Tree node, t, the parent, and comma, tree node. This is not valid Java by any means. And then the actual child, right? I want to find the node and its parent at the same time and return both of them. And the interpretation here would be that if child is null, well, at least you have the parent here and then you can insert it as that child. Otherwise, it's not null, and that tells you it's here and here's the parent. Right? And I thought that would be really, really nice. And so I thought, well, I remembered that there was a proposal at one point to introduce tuples in Java. Whatever happened to that? And I started going down the rabbit hole because I looked up Java tuples, and the first 10 hits are all these, these crappy, clickbait sites. There we go. Clickbait sites with basically the cut and pasted code of, yes, here's a library to do it. Right? They never actually say what the library is, and they never point out the fact that it's not in Java. It's this third-party library. But anyway, then I went to Stack Overflow and asked, whatever happened to that proposal? Because and so I found something, and I found the back and forth debate on why they rejected the proposal. Right? And it's actually it's exactly what I would have said as well, that allowing that kind of stuff natively in your language encourages you to have bad abstractions. Something like this you can do in Python. All it is creating a list, right? And a tuple is nothing more than a list. And you can do that in Python, but then it encourages you to do that everywhere and not to have to write the actual classes to model the problem that you're trying to solve. And I thought it was a very, very good argument. But in any case, I thought, well, in this particular case, it would have been nice. Right? That's all right because you can always write your own pair class. You can always write your own triple class. You can always write your own quadruple, quintuplet, ... Right? Why are you doing it at that point, right? Why aren't you creating a class to model that problem at that point? Right? So, but that would have been nice. Right? In this case, though, if it already contains it, we return it and do nothing. Otherwise, we find the parent of the node if had it existed, and we set all this stuff. Now let's go ahead and test this again, over and over and over again. And sometimes we might get a duplicate, in which case we simply return, right? But that's officially a no operation, right? Instead of accidentally a no operation, no op. There we go. There, that looked like one of them, except there are a lot of single-digit numbers there, right? Et cetera, et cetera. Okay? But they're all sorted. Right? You could go ahead and do some load testing here. Let's go ahead and put in 10,000 values, right? But they'll be between small. I'll keep them small here, between 1 and 100. Right, there we go. Wait, oh yeah, no duplicates. Why? Yeah, we never allow duplicates. And so if you're doing 10,000 between 0 and 99, there's a high probability that you're going to get them all, right? So let's up that to 100,000. Probably not going to get any duplicates there, but also I'm not going to go through and read that all, right? Okay. So some pretty good load testing or fuzz testing, whatever you want to call it there. Right. Nice. So far. All right. Binary. We've got our add method. We've got our find method. We've got our parent method, or that's private. Our contains method, and our in order traversal method. You know what? I don't want to have to call it in order traversal. I just want that to be the default. Put it in a toString method, right? Public string toString, and by default we'll just go ahead and call the in order traversal and stringize it. This dot in order traversal dot toString. Oops, toString. Return that, and I will get the same results. Right? I could make this one. I think that we made the binary tree. I think we made it. Oh, we didn't. Oh, no, we did. It's just a different version. We made that iterable, right? All right. So what's missing here? CRUD, create. We can put stuff in. Add, retrieve, right? Contains is good enough. But if contains is not good enough, then we'll go ahead and do a full in order traversal for you. Retrieve, that's R. Update is nothing more than find it, delete it, and replace it. Okay. So the last one, D. Delete. Okay. Public remove T item, or X, I guess. And it's void. Okay. Well, first of all, if it doesn't contain it, can you remove it? Nope. So, say what?
If it doesn't contain it, try and remove it.
We could throw an exception. We could return, instead of returning void, we could actually return the item, right? And then we could return null to give even more information, right? It didn't exist, right? But then that raises a question of, do we allow nulls or not? And apparently we are allowing nulls. Let's go ahead and go void here. What's going to happen if we do allow nulls? Let's go over our demo here. We've put in 10 random values, but also then bst.add null. Let's try it. Yep, null pointer, but where? When it tries to compare them. Right? Oh, okay. Then let's go to the new school Java. Right? I asked you to remind me, and that just reminded me. Right? Comparator for integers. Integer. Right? C is equal to, or CMP, I guess, is equal to comparator. There's a builder pattern with modern Java. Dot comparing what? Integer dot, or the value of function. There we go. There. There. That's how you can do it. Well, I wanted it reversed. Reversed. Dot. Then, oh no, what are you doing? Dot. Come on. Compare. What are my other options? Darn it. Does anybody remember? Dot. Yeah, there's reverse order. Why are you comparing dot reverse order? Why are you not letting me do that? I've got it somewhere. All right, ignore this. where's the account account report? All right, by name. There we go. That's what I wanted. Why are you not letting me do that? Get rid of that. Comparator, blah, blah, blah. Comparator comparing integer value of. Okay. Then comparing. It should be allowing me to do this. Comparing integer value of. And then it should let me chain it. I don't know why it's not letting me chain it. Value of. Oh, that's okay, because that's the static method, isn't it? All right, so we should use a different function. Dot. Let's go open that class up. What would give me the value of it? I'm not going to get anywhere with this. Integer dot value of. No, it's not value of. So dot. How do I get the integer dot int val? There is, but it won't return the actual int val. Nope. Dot double val dot. Get integer. Nope. Those are static methods. Parse, reverse, signum, toString. Oh, I'm not going to be able to do this then, am I? Fine. Integer dot. Isn't there a comparator? Darn it. What is it going to be? I need it to return like a getter, basically. And off the top of my head, I don't know what it's going to be. These are all max, number of leading zeros, parse int, reversed, sum. Oh, to int, to unsigned long. No, these are all static methods. I don't want any static methods. Because it won't let me, I can't use the static methods. All right, so I need an integer y. There we go. And then I can go ahead and let's get rid of all this stuff for just a second so that it compiles y dot to string to unsigned compare to. That's toString is not going to let me do it. It should be int dot int value. There we go. That's what I thought it was. Didn't it work? That should work. There. Then compare reversed, right? Then you can go reversed, or what? Okay, so back to what I was trying to do. Nulls. How do you handle nulls? Dot nulls. What? I should have done this before it came. There should be like a nulls first, isn't there? Ignore nulls or something. Oh well. Anyway, there's the best I could do. Sorry. There. That's the new school way of doing it, right? But then you could chain it, right? You could then chain it, and if they're equal, then if it's something other than integers, if it was like accounts, you order it by the owner's first name or last name, then ordering by first name, then ordering by account ID or whatever, right? And that's the idea there. I thought that there should be like nulls. Okay, fine. Anybody have it? Ignore nulls or nulls. I thought it was nulls first or something. Dot nulls. Oh yeah, there we go. Nulls first. Why can't I chain that though? screw it. Anyway, now this still won't work because I am passing in null. I thought you could do nulls first. I mean, I tried, and then it dot nulls first, but it's going to take another comparator. Nulls first, nulls last. So what I mean, I could do it, but I just can't chain it. Comparing, and then CMP is equal to CMP dot nulls comparator dot nulls first CMP. I'm just, why do I have to create it and then destroy it and then? Yeah, that's what I had to do, right? But then why can't you can chain that? You should be able to chain that. I'm not sure why. That's a design inadequacy, not a flaw, but it's something that would have been nice, so that I didn't have to take two comparators and wrap one of them up in a nulls first. It probably has something to do with how it actually gets implemented, and it has to wrap it up because it needs to call the other one as a callback or something. But in any case, we see that it works now, and null becomes first. You can wrap it up into a nulls last, and then that null will be at the very end. All right, big deal. That's eaten into our time to actually go about removing, right? So again, if it doesn't contain it, it's not the case that this tree contains X, then go ahead and just return. Right? Or a better way of doing that is actually getting the node, tree node T. I'll call it U, right? Or I'll call it, yeah, I'll call it U. This dot, what was it? Find node of X. Right? Now, if U is null, then you know immediately that it doesn't exist, and so just return. Right? Otherwise, it does exist, and now we can proceed to delete U. Right? Delete U, dot, dot, dot. So, has anybody watched the new Batman on HBO? All right, I did on HBO. And the villain is the Riddler, and he one of the riddles is you are El Rata Alaro or something like that, and they don't understand what it is, and then somebody else points out that no, that's terrible Spanish. It's not El Rata, the rat, right? It's La Rata, and oh, that must have been intentional. So read that again. You are El Rata. They needed to type in a URL, rata.com or something like that. I thought it was absolutely ridiculous. URL Rata? URL? Uniform Resource Locator? Come on. That just took me out of the moment and like, this is not as good as I had hoped. Anyway.
Does it get worse then?
Some of the performances are kind of bad. Because they're kind of like stereotypical Guido kind of performances. Like, yeah, okay, you all like The Sopranos, apparently. Anyway, we need to delete U. So if U is a leaf, what can we do? If U is a leaf, then just delete it, right? How? By setting its parent to null, right? U dot set left child to null, or is it U dot set right child to null? Which one is it? Well, first of all, how do we know that U is a leaf or not? Oh, sorry, U dot get parent. There we go. We're going to have to change it anyway, no matter what, but first question first. How do we know that U is a leaf? Hey, we implemented that, didn't we? How did we implement that? It doesn't have a left child and it doesn't have a right child. Convenient, right? So if U is a leaf, we just need to get its parent and either delete its left child or its right child. How do we go about doing that? If U is, here's another opportunity, not Batman, but a classic 200-year-old riddle, another riddle. All right, so I'll just give it to you in word form here. This man walks up to a painting of a portrait and says, I recognize this person, right? Brothers and sisters, I have none, but this man's father is my father's son. So here's the painting. Who is it? So brothers and sisters, here's the man looking at the painting. Right? Brothers and sisters, I have none. But this man's father is my father's son.
Oh,
It's him. Right? It's a portrait of him. He's just looking at a mirror. Ha ha ha. All right. So how do we know that you is a left child or a right child? We have to answer that riddle, right? If u is equal to u dot get parent dot get left child, right? I'm getting my parent and I'm getting the left child and I'm asking, is that me? Right? Then I'm the left child. Yeah.
What if, that's next full second maybe. But if this man's father is my father's son.
This
so-
man's father is my father's son. Therefore,
And this man's father is me. So it's my kid.
nope. This man, so here's the portrait. This man's father is my father's son, which is me.
I don't care what you meant.
Yeah.
I got it now. Like, when you do this, 'cause it was, I don't know, there was just something about it.
Yeah, it's just a stupid riddle. And there's the riddle, there's the Java implementation of that riddle, right? In fact, I don't like this at all. Let's go ahead and go into the binary tree node. Where is the binary tree node? And let's put that in there, right? Public Boolean is left child, right? And public Boolean is right child. Because I don't want to have to suss out that riddle in my head every single time I ask that question. So how do I know if I'm a left child? If, careful, what if the parent doesn't exist? If the parent is not null, right? And you can get the parent, this dot parent dot get left child is me. And so if parent this dot parent is not null, then you can get it, and then you can get its left child, and it's equal to me, right? Then return true. So just return this.
Isn't that still going to give you an error if the parent is null?
Yeah.
Because then you're calling.
So if the parent is null, short circuit. This is false. Does this thing get executed at all?
Okay.
Nope. Right, that's the beauty of short circuiting. Right? And that's why every single programming language ever, except for 2 or 3 that nobody cares about, does short circuiting. So you can do null pointer checks like this. Right? Now it's not you, but it's this. Right? Now here's another question. What if the left child is null? That's okay. Is null equal to this? I wouldn't exist to ask that question to begin with. So existential riddles in Java code here, right? If I don't exist, can I ask the question of, do I exist? No. Goes all the way back to, who's there? I think therefore, cogito ergo sum, I think therefore I am.
Descartes.
Descartes, is it? Or, yeah, probably Descartes. And for the right child, it'll be right child. Right? I think I'm this, therefore I am. Right? I couldn't ask that question otherwise. Excellent. Now, if it's a leaf, now this gets greatly simplified, right? If u dot is left child, then I will simply delete the left child, right? So u dot get parent dot set left child to null. Right? Else, if u is a right child, then I do a u dot get parent dot set right child to null. There we go. Yeah. Why did I do an else if? Oh, why did I make that second check? because there's a third option. What if it's not a left child? What if it's not a right child? What if it is a root? Right? Else, then there would be no parent, right? So this would be null, and there would be a null pointer check, null pointer exception when I try to set its left child, right? I am the root, therefore I have no parent. So if I'm deleting the root and it's a leaf, what kind of tree is that? It's just one node, right? We call that a seed. And so what do I do? Delete the root. Right? So this is case one. Else if, right? U dot num children is equal to 1. Then do that to do, right? Else 2 children to do. Right? I don't have num children, do I? But that's a gift that I can give to myself. Public int num children. Right, return what? So if it was a language like PHP, you could marshal null to be 0. You could just add them together, right? It's kind of cool, but then when you realize that it's PHP and that comes with all sorts of other problems, right? Then it becomes less cool, right? Int count, we'll just do straightforward here, right? If this dot has left child, then count plus plus, right? If this dot has right child, plus plus, return count. I like that. Good enough. And in engineering, what's better than good? Good enough, right? All right, so if it has one child, I left that as a to-do, you do it. Right. If it has children, I left that as a to-do, you do it, except that I will give you a little bit of a hint. Right? What do we need to delete 50? We get rid of it, remember? And then what can we replace it with? The maximum number in the left subtree, 49, or the minimum number in the right subtree. So what I will do, though, is I will give you an implementation to get those. Private tree node of elements of type T, get min, rooted at tree node U. Right. So the idea to this is that if I gave you a node in the tree, right, say this node right here, you would get the minimum among all of these, or max, right? If I gave you this node, I want you to get the maximum, which is going to be 49. Now, if it's minimum, what am I going to end up doing? What is the minimum of this entire tree? You start at the root, and you go where? All the way left until there is no left child. To get the maximum, you go all the way right until there is no right child. So, get min, tree node, T, right? Current, started at U. That's why I gave you U here. You don't just start at the node. You can start at any node, and from that node, just keep going left or right, depending on min or max. Right. Start at U, while current dot has left child, go to it. Or get left child. Right. And return current. Why do we stop short? Has left child here? Because we don't want to fall off the edge of the tree. If you have no left child, then stop right there. That's the last node before you fall off. And what would get max look like? Has a right child. Note here, I'm not even bothering to use my comparator, am I? Because I am trusting the structure of my tree. Right? I made it private because it returns a tree node, and I don't want to expose that, a leaky abstraction. But of course, we could wrap that up to test it public t get min. Right. What would that look like? Tree node t minimum node is equal to this dot get min, oops, of this dot root, and then return minimum node dot get item. Right. What would get max look like? Yep. Max node get min goes to get max. Let's test it out. All right. Oh, there's a good question here actually. What will be the minimum? And what will be the maximum for this tree that I just made? Null will end up being the some random value for the minimum and then null for the max because I allowed nulls. What if I don't put in null? Then it'll actually give me that value there, 5 and 76. Right. So again, how would you use these in your to-do here? You have two children. Go to the right child and find the minimum. Go to the left child, find the maximum. That's what you promote up to the top. Now you just have to delete that node. Right? In fact, I'm thinking that I want to redesign this as a result and have a private void delete node, tree node t u. There we go. And what I'll end up doing is deleting u under the assumption that it has at most one child, right? Or something like that, right? Because then I could reuse that, right? I wouldn't have to have that. Eventually I'm going to promote that element up and then that node now needs to be deleted. Okay, well, I'll just make another call to delete node on that node and it'll take care of the logic for me, right? So, to do. Right? And I leave that in your capable hands because on Thursday we're going to look at another tree called a heap. Right? All right. No questions online? All right, then have a good Wednesday, I guess, middle week.